Hi children, how are you doing? Today we're going to discuss about a very important topic called torque or moment of force, and this is very important for both the ICSE and IGCSE syllabus students, especially around the 10th grade. Okay, there are tons of numericals that get covered in this topic. So once we understand torque, we'll also investigate into the concept of principle of moments, okay, and we'll solve some numericals around that. So here we go. So let's talk about moment of force. Moment of force is also called as torque. Okay. So what is this moment of force? To explain this, let's consider this example, right? Let's say you have a seesaw and we have a boy who's sitting on one side, right? When you say seesaw, we know that seesaw is pivoted in the center. Pivoted means the seesaw can move left or right based on the pivot. It's fixed, right? And then the boy is sitting on one side. What do you think will happen? Obviously the seesaw will tilt towards the direction where the boy is sitting, right? So this tilting or the seesaw rotating is because of moment of force, right? So there are two things that are important for computing the rotation. One is, what is the weight of the boy? What is the force that is extended in the seesaw? Point number one. Point number two is, at what distance this person is sitting from the pivot. Okay, so these two things are important. So we define this moment of force or torque as a product of two things. One is the weight or the force, and then the perpendicular distance from the axis of rotation, or perpendicular distance from the pivot. That is nothing but the definition for moment of force. Alright, so now we have understood what you mean by moment of force or torque. We need to investigate the units of this. Units of this will be force, Newton, multiplied by distance, meter. So the units of torque will be Newton meter. So what is torque? Torque, is it a scalar or a vector, right? Torque is a vector. Torque has direction, right? So how do you find this direction? Okay, so when we say that the force is acting in this direction and the rotation, the beam is moving here in this direction, we say this is a anti-clockwise moment. Okay, if the boy is sitting on the opposite side and the beam is moving down, we say this is a clockwise moment. When the rotation is happening in the direction of the way the clock moves, okay, so we call that as the clockwise moment. If it is opposite that, we call that as the anti-clockwise moment. Okay, so two types of torques are there. But how do we denote this mathematically? Okay, so for this we have what is called the right hand rule. So you take your right hand and then you curl the fingers here. Give me a big thumbs up. And then what you do, you look at the curl, the direction of the curl of the fingers from the top. So here, when you're taking a right hand and looking from the top, when the thumb is sticking up, you see that the curl of the fingers is in the anti-clockwise direction. Okay, so this is the anti-clockwise torque that is happening. And if you see, the thumb is pointing towards top. So we say torque is in the upward direction when you have an anti-clockwise moment. I hope you understand this, right? So now let's consider the opposite. Supposing the turning is in the clockwise direction. If the turning is in the clockwise direction, you have to keep your hand reversed. And you see here the curl of the fingers. The curl of the fingers is now moving in the direction of the hands of the clock. And you see the thumb is sticking down. Okay, so whenever we have the clockwise rotation or clockwise moment, we designate it as a negative. It is in the downward direction. We say torque is in the negative direction. Okay, so upwards torque for anti-clockwise, downwards torque or negative torque for clockwise moments. I hope you understand this. Now that we've understood what we mean by torque or moment of force, let's understand the next concept, which is called the principle of moments. Okay, so if before we go into principle of moments, we have to understand objects in equilibrium, right? So supposing we have a rod, or you can say a beam, and we say, yeah, we want this beam to be in equilibrium. What are the conditions for the beam to be in equilibrium? Okay, so essentially two conditions. The first condition is algebraic sum of forces acting on the beam should be equal to 0. What do we mean by this? Supposing we are applying force in the upward direction. There are two forces acting in the upward direction. The weight of the beam is in the downward direction. We say that the beam is in equilibrium if the forces in the upward direction equal to the forces in the downward direction. Okay, so upward forces we can take it as positive, downward forces we can take it as negative. Both have to be balancing each, or the summation of all of this has to be equal to 0. That's what we mean by algebraic sum of forces is equal to 0. That's condition number 1. What's the second condition? The second condition is if this beam is pivoted such that it is going to rotate, right? Algebraic sum of moments of forces of around the beam, on the beam, has to be equal to 0. What do we mean by this? If the forces are such that they are going to cause a anti-clockwise moment, and if there are some forces which are causing the clockwise moment, right? So overall the torque on the beam has to be equal to 0. Okay, that means the clockwise moments of force should be equal to the anti-clockwise moments of force. Algebraic sum of torque has to be equal to 0. If these conditions are met, then we say that the rod, the beam, the object is going to be in equilibrium. I hope you follow this. All right, so while we were discussing about moment of force, we said that the moment of force is equal to force and multiplied by the perpendicular distance. Okay, so there is some clarification is required in this so that you don't make a mistake. Later on, when you learn about vectors, you define torque as a cross product. Okay, I'm just telling it to you now. So we say torque is equal to R cross F. This is the actual definition, but now we don't have cross products, so we come up with a very simple definition that torque is nothing but force into multiplied by distance perpendicular, R perpendicular. So this is what we will learn in 10th standard. So what do we mean by R perpendicular? That's what we are discussing now. So if I have this force here, and this is our distance R or D or whatever, right, from the point of the pivot to the point of application of this force, right? P is where the force is being applied. We see that the force is applied in a perpendicular manner. Okay, so you have this and the force is acting in a perpendicular manner. Okay, so in this case we can say torque is equal to force into F into D. If you say torque is equal to force into distance, this is going to be true. Okay, but if we are not applying the force in this direction, we are applying force at an angle. Okay, so we have this beam here. Instead of applying the force like this, we are applying the force at an angle. Then this formula, torque is equal to force into D, will not work. Okay, so let's examine that in detail. So this is the case that we are discussing. So we have the force. Force is not acting perpendicular to the beam. In fact, it is making an angle theta. How do we calculate this? Okay, so we come to the resolution of forces, right? So if you have not seen that, please look it up. I have made a separate video how to resolve forces, velocities in horizontal and vertical directions. Okay, so now what we have to do is we have to resolve this force, or we have to find the component of this force along the vertical. So this is the axis that is perpendicular to the beam, right? So what is the projection of this fellow onto this vertical axis? That's what we need to calculate. How do we do that? We just take the shadow of this on. That means we have to calculate this length. Okay, so if you take this as a triangle where this is P and this is O and this is Q. If you take this triangle, if you find out PQ is going to be the perpendicular force, the force that is acting in the perpendicular direction, or the vertical component of the force. So how do you calculate that PQ? So I've just kind of drawn this diagram so that you can visualize this clearly. So the same force is here. This is F out here, OP, and then we have to find out this PQ. PQ happens to be the vertical component of force. We need to find this. So if you consider this triangle RPO, okay, what is sine theta going to be? So sine theta is going to be RO divided by F, isn't it? So let's write this down. In triangle RPO, okay, we see that sine theta is nothing but opposite side, which is OR, divided by our hypotenuse. Hypotenuse is OP, but that OP happens to be equal to F, okay. So we say sine theta is equal to OR by F, or OR therefore, which is what we want, is nothing but F into sine theta, okay. So that means we have calculated OR and PQ will be one and the same, okay. Therefore this is going to be, this pen is not writing, I'll just change it. This PQ is going to be F into sine theta. So whenever we see that you have a force which is acting at a direction, and the theta between the beam and the force is given, we have to be careful as to what this angle, what is the specification of this angle. If it is in this direction, F, we simply take F sine theta, and now that we have F sine theta multiplied by D is going to be torque, okay. So torque is now going to be F sine theta multiplied by D, okay. So this is how we take the vertical component of force in order to compute torque. I hope this clarifies. So let's reiterate what we've learned by working on this simple problem. We have a force given 10 Newton and we have been specified the angle. We have to find the torque or moment of force because of that 10 Newton force. How do we do it? If you say torque is going to be equal to 50 multiplied by 10 sine 30. Okay, do you think your answer is going to be correct? The answer is going to be wrong. Reason is, when the theta was given as this between the beam and the force, then you can apply directly F sine of that given angle, F sine theta. But here this angle has been given as 30. So this is the alt concept. You have to be very careful. Just like when they give you the angle of incidence, right? They will say that this is the normal, and they will specify this theta 30 degrees. You will say angle of incidence is 30 by mistake, but angle of incidence is always with respect to the normal, isn't it? So we have to be careful what is that correct angle that we have to assume, okay? So here, though this 30 is given, the actual angle for us will be 60 because this happens to be perpendicular, okay? So we will have to say torque is nothing but torque here is going to be 10 into sine 60 multiplied by this 50, okay? And we do know that sine 60 is root 3 by 2, so it will be 10 into root 3 by 2. And if you want to be very particular about the units, this 50 centimeters is nothing but half a meter, okay? So you can replace that as half into half. So this is going to be 5. So 5 by 2 into root 3 Newton meter. So this will be the correct answer. I hope you understand this. Now that we have understood what is moment of force, equilibrium, let's get started with the numericals. So look at this numerical. In this numerical, the mom is making a toy, a simple balance for the child, and you have an elephant on one side and you have a monkey on the other side. we have to find out what's the weight of the monkey. Okay, so let's tabulate the values that are given. So this, as you know, is a simple moments problem where this is the weight of the elephant. It's given as 0.6 Newton, and this is the weight of the monkey. Let's keep the weight of the monkey as weight of the monkey. The numerical can be represented in this way. So 0.6 Newton is the weight of the elephant. It's at 8 centimeters from the pivot. This is the pivot. Okay, so you can consider this is around this point the beam can rotate. So if the beam has to be stationary, we'll use the principle of moments, right? So we find that the elephant is going to have a torque. What kind of torque is this? This torque is going to go like this. This is anti-clockwise, okay? And this monkey is going to have a torque in this direction. So this is going to be a clockwise torque, right? So if the beam has to be in equilibrium, what we need to do, we say that clockwise torque has to be equal to the anti-clockwise torque. We are using the principle of moments here. So we say 0.6 into 8 equal to W, weight of the monkey, into 16. Or we can say the weight of the monkey is going to be 0.6 into 8 divided by 16. 8 2s are 16. This will be 0.3 Newton. So the weight of the monkey is 0.3 Newton. Simple. Alright, so this is the explanation for the second numerical. What is this? Here he is asking us, this is a meter scale, right? So whenever they say meter scale, its length is 1 meter. Okay, you have 0 on one end and the other end is going to be 100 centimeters. Therefore the name meter scale. Now here there are 3 weights which are given, and he is told that the meter scale is pivoted at the 50 centimeter mark, means it's balanced. So if you add weight on one side, the meter scale will rotate. It is experienced unbalanced torque. What this guy is telling is that there are 2 1 Newton weights suspended at the 60 mark and the 80 mark, and he has given us a 2 Newton weight. He is asking us to hang it from this side such that the bar is in equilibrium, right? How do we do it? We rely on the principle of moments, right? So we need to find out this particular distance, at what distance this weight is hung, okay? Now while taking this distance, don't do the mistake of telling this is at 60, right? So we need to compute this distance out here. This distance is 50, 60 means this is 10, and this is at 80 from this point means this is 30, right? So be very careful as to how we take the distances. It should always be from the pivot, right? So once again, if you see here, we use the principle of moments. This is going to be the anti-clockwise moment for us, and there are 2 clockwise moments. One is because of this fellow and the second because of this fellow, right? So anti-clockwise is equal to clockwise. Clockwise moments. So this will be 2 Newton into x is equal to the sum of the clockwise moments, 1 into 1 Newton into the first distance, which is 10, plus again 1 into 30. Okay, so x is going to be equal to 10 plus 30 is 40 divided by 2, that is 20 whatever, centimeters or whatever, right? So if this x is equal to 20, at what distance is it to be hung, right? So the overall thing is 50. From this is 20. That means this has to be hung at the 30 centimeter mark. So it has to be, either you can, if they ask us to mention this distance, you can say it's 20 centimeters from the pivot, or it has to be hung or suspended at the 30 centimeter mark. So once again, this is the you're using the principle of moments in order to find the distance. So there are some of the problems in this topic where they'll ask us to find the reaction. Okay, so we need to understand what we mean by reaction or reaction, forces of reaction. So let's take this our seesaw, and let's say the weight of the seesaw is 10-20 Newton. Okay, and assume that this weight is acting, it's a uniform seesaw, it will act in the center. And at the center we have this pivot. Okay, so if you draw the free body diagram is a diagram where we put all the forces which are acting on the object. Okay, so if you draw the free body diagram for this and consider this pivot as a point, so we see that the weight is going to act on the pivot, which is 20 Newton. And this pivot is going to give a reaction. That reaction will be in the opposite direction. Okay, so this is also going to be 20 Newton, right? Why this reaction is coming? Well, that's a separate topic. It's got to do with the atoms and molecules in the pivot, normal reaction. So we will discuss that separately. So the problems that will involve around reaction will be of this nature. Okay, they will say that this is a beam and it is simply supported at its edges. Okay, simply supported means there is some support out here, there is yet another support out here. We can call this as point A and B, and like here we had only one reaction, here we may have multiple reactions, right? So here we will say wherever there is a support, there is a reaction. We will say reaction at A, and here we will say there is a reaction at B. Okay, so they may give us a system of forces. Okay, they may give us a weight, and they will say that if this beam is to be in equilibrium, find out what is the reaction of these forces. So we'll try to solve a numerical of this type. So in the numerical that was shown to you, it said that the weight of the beam is acting at a point which is 4 meters from one edge, and it is given as 6 meters. This is 6 meters, and it is supported on both the ends, and we are asked to find out what is the reaction at A and reaction at B. Okay, and the weight of the beam which is acting is given as 100 Newton. Okay, so basically this will be the way we represent it. Okay, so it's given that the beam is in equilibrium, so here we have to use both the conditions, right? The first is the top forces in the upward direction equal to the forces in the downward direction. If you look at it, both the reactions RA plus RB is going to be equal to the downward force, which is nothing but 100 Newton. That's our first equation. And to find out either of this, right, what we do is we assume any one as the axis, right? So let's take this as an axis, and we find the moments about this axis and say that overall moments is going to be 0 because the beam is in equilibrium. You can choose this as an axis, you can choose this as an axis, or you can consider an axis in between. It depends on us. Okay, so in this case let's consider this as an axis and take the moments. Okay, moment of RA about its own axis will be 0, right, because there is no distance. What about this? This is going to be a clockwise moment, and this is going to be an anti-clockwise moment. Okay, so you can say taking moments about A we have 100 into 4 will be equal to RB into 10. Reaction at B multiplied by 10, we can find out RB. Reaction at B is nothing but 10 into 4, which is 40 Newton, right? So the minute you have reaction at B as 40 Newton, we can immediately use this relationship, RA plus RB is equal to 100, therefore RA has to be equal to 60 Newton. So in this way, even if they are giving you numericals where we have to find the reaction, based on the simple moments, taking the moments, we can assume axis around the reaction forces and find out the reaction. So there's one concept which you need to know called a couple while we are discussing the moment. Couple is nothing but two equal forces, okay, F and F, which are acting on an object, but they are acting in upward direction. Here is an upward force, there it's a downward force. So together these guys constitute a couple, right? So COUPLE, this is the concept we are discussing. How do you compute that? For computing this, we simply take any one of the force, okay, and we say couple is equal to any one of the force multiplied by the distance between the forces, D, right? So that is the definition for a couple. That is the overall moment of the object is what is called a couple. If you want to, we can consider this as D by 2. So we say, hey, this is going to be a anti-clockwise moment, F into D by 2. And once again, this is also going to be an anti-clockwise moment. This also is F into D by 2. So overall moment of this member is going to be F into D by 2 plus F into D by 2 is 2F into D by 2, which is nothing but F into D, okay? So that's what is called a couple. So if two equal and opposite forces are acting on an object such that the object can rotate, the couple is nothing but the one of the forces multiplied by the overall distance between the force, F into D. So that's what is couple. Alright, so here we have a steering wheel, and we normally for steering the wheel we apply forces, isn't it? So the forces we apply on the hands will be, if I am moving this up, this hand will be down, only then I can turn the wheel. So essentially this constitutes a couple, right? So supposing I am gripping here, I am applying a force in this direction, right? So let's say 10 Newton, and I am holding my hand in the opposite direction, applying a downward force. Assume that also is 10 Newton, right? If we are asked to find the couple on the steering wheel, all we need to do is we need to multiply the force multiplied by the diameter of the steering wheel, okay? So if they say the diameter of the steering wheel is, let's say 0.6 meter, right? So the couple on the steering wheel will be 10 multiplied by the dia, which is 0.6 or 6 Newton meter. That's about couple. Thank you so much for watching our videos. Please like and subscribe to our channel. Be sure to share it with your family and friends, and don't forget to visit our website www.cogitarelearning.com, where you have linked to all the videos that we have been recording so far. Thank you once again.